hi, hello, how are you? This is Gopal. Today we are going to discuss lecture number 7. Rotatory motion, lecture number 7. So in lecture number 6, we discuss moment of inertia for a continuous bodies. In lecture number 6, we can discuss moment of inertia for continuous bodies. So first one is rectangular lamina, So rectangular lamina moment of inertia I is equal to ml square by 12. So second one, we discuss triangular lamina, so moment of inertia I is equal to ml square by 12. So second one, triangular lamina, so I is equal to mh square by 6. Third one, so solid cone, moment of inertia I is equal, moment of inertia I is equal to 3 mr square by 10. So next one, fourth one, so hollow cone moment of inertia I is equal to mr square by 2. So in lecture number 6, rectangular lamina, moment of inertia I is equal to ml square by 12. Triangular lamina I is equal to mh square by 6. In solid cone, moment of inertia I is equal to 3 mr square by 10. Hollow cone, moment of inertia I is equal to mr square by 2. So in lecture number 7, we discuss there are two general principles or theorems. One is perpendicular axis theorem, second one is parallel axis theorem. So in lecture number 7, you can discuss there are two general theorems. One is perpendicular axis theorem, second one parallel axis theorem. When lecture number 7, we can discuss there are two general theorems or principles. In lecture number 7, we can discuss there are two general theorems or principles. There are two general theorems, principles of moment of inertia, which sometimes has to determine the moment of inertia of a body. Moment of inertia of a body about an axis. When the moment of inertia about some other axis is known. There are two general theorems or principles of a moment of inertia which sometimes enables us to determine the moment of inertia of a body about an axis when the moment of inertia about some other axis is known. There are two general principles. First one, perpendicular axis theorem. Perpendicular axis theorem. Perpendicular axis theorem. This theorem is valid only. This theorem is valid only for two-dimensional objects. Only for two-dimensional objects. This theorem, perpendicular axis theorem, is valid only for two-dimensional objects. Like two-dimensional objects like lamina, plate, and seat. Suppose I will consider the one object. So this is center. So this is what x-axis. This is x-axis. This is y-axis. And this is z-axis. X, Y, Z axis. So conditions for perpendicular axis theorem. What are the conditions? There are three conditions are there. Conditions for perpendicular axis theorem. First condition, x, y, z mutually perpendicular to each other. This x, y, z axis perpendicular to each other. So here x comma y comma z are perpendicular to each other. Mutually perpendicular, should be mutually perpendicular. Second one, x and y, here x and y should be in the plane of lamina. Third point, here z-axis should be perpendicular to plane of lamina. There are three conditions. X, Y, Z should be mutually perpendicular. Second one, x and y axis should be in the plane of lamina. And the third one, z axis should be perpendicular to plane of the lamina. This z axis should be perpendicular to plane of lamina. Means these two x, y, z axis should be like that, perpendicular to plane of lamina. Suppose you can write this is y. So this is y. So z should be perpendicular to the plane of lamina. This x and y axis should be in the plane of lamina. Z axis should be like that, perpendicular to the plane of lamina. Z axis should be like that, perpendicular to plane of lamina. So we can, what is the proof? Proof of perpendicular axis theorem. So here one more note, one more point, note this. Here all the three axes, all the three axes, all the three must intersect each other, must intersect each other. At a single point, and that intersection point, intersection point need not be center of lamina. So all these three axes must be perpendicular, intersect each other, and at a single point, and these three intersecting point need not be center of the lamina. So this is the condition. So next proof. Proof of perpendicular axis theorem. So I will consider, so this is a point, this is one point. So from x-axis to, from x-axis to, so this distance I will consider y. From y-axis, so this is along the x-axis, so this is along the x-axis, so I will consider this x. So this point is from this origin to this distance is I will consider r. So can I write here, so this is x, means this is also x. So can I write r square is equal to x square plus y square. R square is equal to x square plus y square. So this is along the x-axis, this is along the y-axis, this is the resultant. Resultant r square is equal to x square plus y square. So here along the x-axis dm, so can I write dix is equal to dm by dix. From x-axis perpendicular distance is y, so dm y square. So can I write diy is equal to dm x square. So diz is equal to dm r square. From z-axis perpendicular distance is r. For the z-axis perpendicular distance is r. So can I write, already we know r square is equal to x square plus y square. In place of r you can write x square plus y square. So diz is equal to dm x square plus y square. So can I write dm x square plus dm y square. Dm x square is diy, dm y square is dix. So can I write this one is diy dix. So this is diz. So can I write diz is equal to dix plus diy. So this is perpendicular axis theorem. So for total, so iz is equal to ix plus iy. Iz is equal to Ix plus Iy. This is the perpendicular axis theorem formula. Iz is equal to Ix plus Iy. To Ix plus Iy. So this is the proof of perpendicular axis theorem. So you can see the one or two examples. So based on perpendicular axis theorem. So here example, find moment of inertia of a ring about its diameter. So first you can draw the ring. So this is ring. So this is x-axis. This one is y-axis. So this one is z-axis, Iz. It is perpendicular to its plane. Iz is perpendicular to its plane. So we know Iz is equal to, for ring I is equal to mr square. Iz is equal to mr square. So ring exactly perpendicular to ring, we know formula Iz is equal to mr square. So you can find out based on x-axis. So what is the moment of inertia? So next, otherwise you can based on y-axis, you can find the moment of inertia. Both are same. So this axis passes, x-axis passes through the diameter and y-axis passes through its diameter. X-axis passes through along the diameter and y-axis passes through along the diameter. So can I write, so here both are due to symmetry. This is a perpendicular axis theorem. Perpendicular axis theorem. Perpendicular axis theorem. Iz is equal to Ix plus Iy. So here Ix moment of inertia along the x-axis, moment of inertia along the y-axis is equal to, so that is Id. Due to symmetry, so we can write due to symmetry. Due to symmetry we can write this, both are same. Ix is equal to Iy is equal to Id. So can I write, so Iz is equal, moment of inertia along the z-axis is equal to mr square is equal to, can I write this due to symmetry, can I write this both are same, so can I write 2 times of diameter. So moment of inertia along the diameter is equal to mr square by 2. So this is by using perpendicular axis theorem we can find out moment of inertia of a ring about its diameter. Formula is what? Id is equal to mr square by 2. Id is equal to mr square by 2. So second example, so this is the first example. For second example, example 2, so you can easily find out, find the moment of inertia of a disc about its diameter. Suppose I will consider, so this is the diameter, this is a disc. So by using perpendicular axis theorem, Iz is equal to Ix plus Iy. So Ix is equal to Iy is equal to Id due to symmetry. So what is the moment of inertia of a disc? Moment of inertia is perpendicular to the plane. We know that is z-axis is here perpendicular to the plane. We know I moment of inertia along the z-axis is equal to mr square by 2. Mr square by 2. So substitute here. So in place of Iz, we can write mr square by 2. So I want Id. Id is equal to mr square by 4. So this is about moment of inertia of a disc about its diameter. Id is equal to mr square by 4. This is for disc. Next example, example 3. Find the moment of inertia of a square lamina along that axis passes through its COM, center of mass. So you can find out that axis passes through COM. So this is the square lamina. So of a side is A. All side is A. So this is axis passes through center. So this is Ix. This axis passes through y-axis. center, this is Iy. So these two we know. So here Ix is equal to Iy is equal to ma square by 12. Ma square by 12. Already you find out by using moment of inertia. Ix is equal to Iy is equal to ma square by 12. What is the perpendicular? So here asking is what the axis passes through the COM, you can find out. So this is the axis passes through the COM, that I will consider Iz. The axis is passes through the COM, center of mass. So that axis is, this z axis is going like that. So passes like that. So can I write Iz is equal to, by using perpendicular axis theorem, Iz is equal to Ix plus Iy. So here Ix is equal to ma square by 12 plus Iy, moment of inertia along the y-axis also we know ma square by 12. So 2 times of ma square by 12. So 2 1 ja 2 6 ja. So ma square by 6. The axis passes through center of mass. So Iz is equal to ma square by 6. So this is the third example. So all of you watch my videos, subscribe, share and like my videos. So all of you bye, take care, have a nice day.